Question 1. Which of the following equations correctly describes the relation between power, work, and time? Now, in this situation, we can use some dimensional analysis here and see which equation has balanced units, both sides of this equal sign here. So first of all, we need to find out the units. We need to write out the units of power, time, and work. So work is measured in joules, has units of joules. Power has units of joules per second. And time has units of seconds. And these are SI units. And these SI units must balance on each side of the equation here. So it's not going to be A, because we have joules on this side, and we've got joules per second, which equals joules over second squared. So because these don't balance on both sides of the equation, equation A is not correct. The same is true for equation B, because we've got joules on this side of the equation, we've got seconds in the numerator, and joules per second in the denominator, and that equals seconds squared per joule. So it's not B. Is it C? Well, we've got joules per second on the left-hand side, and we've got joules on top in the numerator and seconds in the denominator on the right-hand side. So I think it's C. Let's just check D quickly. So we've got joules per second on the left-hand side is equal to seconds over joules. And the left and right-hand side are not equal in this case, so it's not D. So the answer here is C. Use the graph below to answer questions 2 to 4. The graph shows the energy of a 75-gram yo-yo at different times as it moves up and down on its string. So we have something like this. So we have a yo-yo initially above the ground at some heights that we don't know, and some final state where the yo-yo has extended to its maximum length, and this is the string. So it's very important to be able to visualize this system here and imagine how the yo-yo is moving throughout these 8 seconds here. And we're measuring 3 things. We're measuring the yo-yo's kinetic energy throughout time, its gravitational potential energy throughout time, and its mechanical energy. And the mechanical energy is simply the sum of the kinetic energy and all forms of potential energy within this system here. Also notice that the mechanical energy does not stay constant over time. It slowly reduces over this 8-second time period. Now, why might this be the case in this system? So this is not a completely isolated system, which means that some of the yo-yo's kinetic energy, as you can see in this white curve here, is transformed into other forms of energy due to frictional forces in the yo-yo and the air resistance it experiences as the yo-yo is in motion. And if it was a truly isolated system, this mechanical energy here would not decrease over time. It would be a straight horizontal line. And the only energy transformation that would occur as the yo-yo is falling down to the ground and back up again would be the energy transformation between kinetic energy and gravitational potential energy in this system. So from 0 seconds to 1.5 seconds, this is where the yo-yo is moving from its maximum height down to its minimum height. And at this point, the yo-yo is moving at its maximum speed because it has its maximum kinetic energy. But then from 1.5 seconds to 3 seconds, it's moving back up to its initial height. because it's losing kinetic energy and gaining gravitational potential energy again. So question 2 says, by what amount does the mechanical energy of the yo-yo change after 6 seconds? So this is the 6-second mark here, and we want to find the change in energy from 0 seconds to 6 seconds here. So initially, the mechanical energy is equal to 600 millijoules. The final mechanical energy after 6 seconds is around about 500 millijoules. Now the change in mechanical energy is equal to the final energy minus the initial mechanical energy. And this is equal to 500 millijoules minus 600 millijoules. And we get an answer of negative 100 millijoules. So our answer is C in this case. Question 3 is asking us, what is the speed of the yo-yo after 4.5 seconds? Well, the only way we're going to find the speed within this system is finding out what the kinetic energy is after 4.5 seconds. Remember, kinetic energy is equal to half times the mass of the yo-yo times its velocity squared. So at 4.5 seconds, we get roughly 350 millijoules. So let's say our kinetic energy is 350 millijoules. And that's equal to half times the mass, which is 75 grams. I'm going to convert this all into kilograms and into joules. So instead of 350 millijoules, this is equal to 0.350 joules, because a millijoule is 1,000th of a joule, and that's equal to half times the mass, which is 0.075 kilograms, multiplied by the velocity squared. We don't know the velocity yet. And we can rearrange this to make velocity the subject of the formula. So let's do that now. So we multiply both sides of the equation by 2 to get rid of this half term here. 2 multiplied by 0.350 joules divided by the mass, 0.075 kilograms. And because we've got a v squared term here, we square root both sides of the equation. So v is equal to the square root of this sum here. So after plugging this into our calculator, we get a value of 3.05 meters per second, which velocity here more closely matches this 3.05 meters per second. Well, the closest one is this A value here, 3.1 meters per second. So that's our correct answer. What is the maximum height of the yo-yo during this 8-second time period? To find the maximum height of the yo-yo, we need to look at the gravitational potential energy in this graph, or the potential energy. Where on this graph is the potential energy at its maximum value? Well, the maximum gravitational potential energy is right at the start at 0 seconds, because this orange dotted line here has a maximum peak at 600 millijoules at 0 seconds right up here. As time progresses, this yo-yo, as it moves up and down, slowly reduces its maximum height. So what is the equation for gravitational potential energy? Well, we learned in a previous lesson that gravitational potential energy is equal to the mass of the object times the acceleration due to gravity multiplied by the height the object is above its minimum 0 point, and that could be the ground. All we need to do is rearrange this equation to make h, the height here, the subject of the equation. So let's do that. So the height is equal to the gravitational potential energy divided by the mass of the yo-yo and the acceleration due to gravity. So the height equals 0.600 joules divided by the mass of the yo-yo in kilograms, 0.075 kilograms, multiplied by the acceleration due to gravity, 9.81 meters per second squared. So summing this up together, we should get the height, the maximum height of the yo-yo here. And what value do we get? We get a height of 0.815 meters. And the closest value here is D, 0.82 meters. So that's our correct answer. Problem 5. A car with a mass m requires 5,000 joules or 5.0 kilojoules of work to move from rest to a final speed of v. If this same amount of work is performed during the same amount of time on a car with mass 2m, double the mass of car 1, what is the final speed of the second car? Now this problem requires us to know about the work kinetic energy theorem, which states that the net work done on an object equals its change in kinetic energy. In other words, work net is equal to the change in kinetic energy, which is equal to the kinetic energy, the final kinetic energy of the object, minus its initial kinetic energy. And that equals half times mass velocity final squared minus half times mass velocity initial squared. So first, we realise that the initial kinetic energy of both cars is 0 joules because the velocity is 0 because we're starting from rest here. So now our work net equation becomes work net is equal to the final kinetic energy, which is equal to half times the mass of the car times its final velocity squared. So if we rearrange this equation to make the final velocity the subject of the equation, we multiply both sides by 2 to get rid of this half term, so 2 times work net. We divide by the mass, both sides of the equation by the mass, divided by mass, and we square root to get rid of this squared term. Square root is equal to the final velocity. Now the easiest way to solve this problem is just to plug in some numbers for the two cars here. We know the first car has a mass of m, and we can say that mass is 1,000 kilograms. The second car has a mass of 2m, which means that it's double the mass. So we can say that's 2,000 kilograms. Now the work done, the net work done on both cars is exactly the same, which is 5,000 joules here, 5.0 kilojoules. So if we got car 1 here, which has a mass of 1,000 kilograms, we got car 2 here, which has a mass of 2,000 kilograms. We already know that the net work done is the same on both cars. So if we know the mass and the net work done, we can find the velocity for these two different cars here. So the velocity, the final velocity for car 1 is equal to the square root of twice times 5,000 joules, the work, divided by 1,000 kilograms. Second car, the velocity of the second car, is equal to the square root of 2 times 5,000 joules, the work done, divided now by 2,000 kilograms, which is twice the mass of the first car. Now we get values of root 10, which is equal to 3.16 meters per second. And for car 2, we get a value of root 5, which is equal to 2.24 meters per second. Now the final speed of the second car, the heavier car here, has a lower value than the final speed of the first car. So let's have a look at our answers up here. Now the final speed of the second car is not twice the speed of the first car. It has a lower value. So answer A is not correct. Now again, answer B is suggesting that the final speed of the second car is higher than the final speed of the first car by a value of root 2. So B is not the answer here. Now C is suggesting that the final speed of the second car is exactly half the final speed of the first car. Now, is this value half of this value? The answer is no. So the answer for C is not correct. But for answer D, is the final speed of the second car equal to the final speed of the first car divided by root 2? Let's plug this into our calculator. So we got the final speed of the first car at 3.16, and we're dividing by root 2. And that gives us a value of 2.2344, which is very close to this value here. So our correct answer is D. For problems 6 and 7, we have this. A 75 kilogram base runner moving at a speed of 4.0 meters per second begins to slide into second base. The coefficient of friction between his clothes and the earth is 0.70. His slide lowers his speed to 0 just as he reaches the base. Problem 6 says, how much mechanical energy is lost because of friction acting on the runner? So where do we start? Well, mechanical energy is the sum of the kinetic energy and the potential energy of an object. And the object here is our 70 kilogram base runner. So in this problem, we're specifically interested in the loss of kinetic energy caused by the work done by friction. The work done by friction is removing mechanical energy from this system as the runner is sliding to a stop. Now, most of this kinetic energy will be converted into heat and sound. And we also need to notice here that there are no forms of potential energy in this system because the runner isn't sliding uphill and neither is the runner sliding downhill. He's moving in a horizontal direction. In other words, he's not gaining or losing height in this situation. So there's no potential energy in this mechanical system. So the change in mechanical energy is equal to the change in the kinetic energy from the initial condition when the speed of the runner is 4 meters per second to the final condition when the speed of the runner is 0. So the change in kinetic energy is the final kinetic energy minus the initial kinetic energy. We know the final kinetic energy is 0 here because the speed of the runner is 0 in the final state. And the runner is at rest at this moment. So the change in kinetic energy is going to equal this term here, this negative initial kinetic energy. And that will be equal to the change in the mechanical energy in this system. So the change in mechanical energy is equal to negative 1/2 multiplied by the mass of the base runner, 70.0 kilograms, multiplied by his initial velocity squared, which is 4 meters per second. 4.0 meters per second squared. And after we sum this up, we get a value of negative 560 joules. And we've got a negative sign here because work is being done to take away energy from the space runner as he's sliding to a stop. If work was being done to speed up the space runner from rest to 4 meters per second, then this 560 joules would be positive because we're adding energy to the system. So we've lost here 560 joules, and this negative sign here implies that we've lost energy. So B is the correct answer. Problem 7 states, how far does the runner slide across the ground? Now we need to remember from the previous question, the change in mechanical energy as he's sliding to a stop is equal to negative 560 joules. In other words, he's lost 560 joules during this sliding process. And in this question, we need to remember what our work equation is and how we can find the kinetic friction when we know the coefficient of friction between two surfaces, which is given here. So let's first start by finding the kinetic friction. Now I've covered this in a previous lesson, so if you need a refresher on static and kinetic friction, I've got a video up here. But the force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal force. So if I draw up a free body diagram here of our runner and show you where the normal force is and how our force of kinetic friction is acting on our runner, it might make things a bit clearer. So that's the ground. This block here represents our runner, and he's sliding a distance of d to the second base. But we're interested in the normal force here, which acts in a perpendicular direction to any surface that the object is resting on. And we also have another force pulling downwards, and this is the weight of the base runner. And that's equal to his mass times the acceleration due to gravity. Now, because the base runner isn't accelerating upwards or downwards, he's only moving in the x direction, this means that these two forces balance each other. They're both the same value. So instead of writing the normal force here, we can instead write the runner's weight because the magnitude of these two values are the same. So I can erase this normal force here and write in mg. And the force of kinetic friction, because our base runner is moving in this direction, the kinetic friction is going to work in this direction and is acting on him to slow him down. Now the work done on our base runner is the measure of energy transferred to or from an object over a distance. Now we're removing energy from our base runner over a distance d. And the formula for work done is equal to the net force working on this object, which in this case is only the force of kinetic friction, multiplied by the distance the object moves over this time period, multiplied by cosine theta. Now, because the force is working in the opposite direction of the object's motion, the angle between the force and the direction of motion is 180 degrees. And cosine 180 degrees is equal to -1. So now we can say that the net work done is equal to negative force by kinetic friction multiplied by the distance. Now we already know the work done during this time period because we worked this out in the previous problem. We worked out that the change in mechanical energy was equal to negative 560 joules because we're taking energy away from this system. We can work out the force of kinetic friction here as well, because we have the coefficient of we've got the coefficient of kinetic friction at 0.70, we know the acceleration due to gravity, and we know the mass of the base runner. What we're here to find out is how far the runner slides during this process, which is our distance d here. So we can rearrange this equation to make d the subject of the formula. So the distance is equal to the work done during this time period divided by the negative of the force of kinetic friction. This equals negative 560 joules divided by 0.70, the coefficient of kinetic friction, 0.70, multiplied by the mass of the base runner, 70 kilograms, 70.0 kilograms, multiplied by the acceleration due to gravity, 9.81 meters per second squared. And this force here is negative, so we've got a negative here. Now when we sum this up, we get a positive value because we've got a negative in the numerator and a negative in the denominator. And a negative divided by a negative makes a positive. So we get a positive value for the distance. And this value is 1.2 meters to two significant figures. And the closest value we get is answer D here. And that's our correct answer. Now in questions 8 to 9, we have a spring scale that contains a spring with a force constant or a spring constant of 250 newtons per meter and a weighing pan with a mass of 0.75 kilograms. During one weighing, the spring is stretched a distance of 12 centimeters from the equilibrium distance or the resting distance. During a second weighing, the spring is stretched a distance of 18 centimeters. So let's draw this out quickly. Stretched by 12 centimeters from the equilibrium position. And the equilibrium position will be the length of the spring if there was no mass attached to the end of the spring. When we add more weight to our weighing pan here, our spring is stretched even further away from its equilibrium position at a distance of 18 centimeters. So problem 8 is asking us how much greater is the elastic potential energy of the stretched spring during the second weighing than during the first weighing. So it's asking us how much more elastic potential energy is stored in this spring with the heavier weight than this spring with the lighter weight. We're trying to find out a ratio here. So first of all, the elastic potential energy in a spring can be determined with this equation. The elastic potential energy is equal to half multiplied by the spring constant or the force constant multiplied by the distance the spring is being compressed or stretched squared. So the distance the spring is being stretched away from its equilibrium position in the first case is 12 centimeters and in the second case 18 centimeters. Now in this problem, the same spring is being stretched to two different lengths, which means that our force constant here is not going to change. We need to find the ratio between the two scenarios here. So to do that, we can write out the potential energy ratio is equal to the elastic potential energy in the second scenario here, potential energy elastic for the second scenario, divided by the elastic potential energy in the first scenario. And that equals half times the force constant multiplied by the length the spring has been stretched, squared, in the second scenario, divided by half times the force constant multiplied by the length that the spring has been stretched in the first scenario. Now we can cancel out the half term here and the spring constant because they're the same in the numerator and denominator. .18 meters in the second scenario squared divided by 0.12 meters squared in the first scenario. Now we can simplify this as 3/2 because the highest common factor in both terms here, if this was 18 and 12, would be 6. 6 goes into 18 3 times, and 6 goes into 12, and 6 goes into 12 twice. So we've got 3/2 squared. If we square the numerator and denominator separately, we get a value of 3 squared, which is 9, and 2 squared, which is 4. So we get a ratio of 9/4 here, which is answer A. So our final question is asking us, if the spring is suddenly released after each weighing, the weighing pan moves back and forth through the equilibrium position, this position here. What is the ratio of the pan's maximum speed after the second weighing to the pan's maximum speed after the first weighing? Consider the force of gravity on the pan to be negligible. Now, intuitively, we know that when we suddenly take off the weight from this second pan here, that this pan is going to have more energy in its stretched spring, which means that when it moves past its equilibrium position, it's going to have a greater speed than the first scenario here, because the spring is not stretched as much as this one here. So we know that the ratio of the pan's maximum speed after the second weighing is going to have a higher value in the numerator than the denominator, because it's going to have a faster speed for the second scenario here than in the first scenario. So when our spring goes from its stretched length, like it is here, back to its equilibrium position, the elastic potential energy gets converted into kinetic energy. And because the force of gravity is to be considered 0 here, we're ignoring it, and this means that no gravitational potential energy is gained as the spring contracts. So we can assume that all the elastic potential energy in this system is converted into kinetic energy. And because of this, we can write that the elastic potential energy for the first scenario is equal to the kinetic energy as the spring moves back to its equilibrium position, and the same is true for the second scenario here. The elastic potential energy for the second scenario in this spring will equal the kinetic energy as it moves past its equilibrium position. So the potential energy ratio here is going to equal the kinetic energy ratio. So the potential energy of the second spring divided by the potential energy of the first spring is going to equal the kinetic energy of the second scenario, divided by the kinetic energy of the first scenario. And that would be the ratio of the kinetic energies as this pan here hits this equilibrium position. And we know that the kinetic energy is half times the mass times the velocity squared. We can cancel out common terms in the numerator and denominator. And this gives us the ratio between the elastic potential energies is equal to the velocity of the second scenario divided by the velocity in the first scenario squared. Now, we already worked out the ratio of the potential energy in the last problem, and that was equal to 9/4. We want to work out the ratio of the velocities now. So if we square root both sides, to isolate the velocity term here, the velocity ratio, we got velocity 2 over velocity 1 is equal to the square root of the potential energy ratio, which equals to the square root of 9/4. Square root of 9 is 3, and the square root of 4 is 2. So the ratio of the velocities is 3/2. So our correct answer is B.